Hi, I'm Nathan. I'm going to talk about approximating the metric traveling salesperson problem, or TSP. And this is joint work with my amazing advisors, Anna Carlin and Cheyenne Oveskaran. In the traveling salesperson problem, you're given as input a list of cities and their pairwise symmetric distances, which form a metric. And the goal is to find the minimum cost tour, which visits every city at least once. And this can either be phrased as finding the minimum cost Hamiltonian cycle, like this, or as finding a minimum cost Eulerian subgraph, so like this. These formulations are actually the same under the triangle inequality. And I'll work with this second formulation here in bold. So we want to find a cheap connected spanning subgraph in which every vertex has even degree, because such a thing has an Eulerian tour. TSP is NP hard, so often we have to resort to approximation algorithms. And the best approximation algorithm has been a 1.5 approximation and is due to Christofides and independently Serdyakov in the 70s. So this is a procedure which runs quickly and outputs a solution at most 50% longer than the optimal one. And unless P is equal to NP, we can't get an approximation algorithm which always gets within about 1% of optimal. So we have some work to do. But there's been a lot of great progress on TSP since this 3/2 approximation. I can't even include everything here. And for example, we know a 1.4 approximation for the unweighted case. So when all the edges of the graph have weight 1. And we even have a PTOS, so an approximation algorithm with ratio tending to 1 as the runtime grows for low dimensional spaces. However, the general case has not seen progress since this 3/2 approximation. I'm going to tell you about some tiny progress on this question. So in this work, we prove that there's a randomized 1.5 minus 10 to the negative 36 approximation algorithm for TSP. I'll start with 2 pieces of background and by defining the algorithm. The first piece is pretty standard. It's this linear programming relaxation for the problem. It asks for basically a fractional Hamiltonian cycle. So this means that every vertex should have fractional degree exactly 2, and every cut should have fraction at least 2. So here's a feasible solution. For example, here's a cut with value 2, and here's one with value 3. And you can see no cuts have value less than 2. And when I say value, I mean you just count you sum the x's of the edges that cross this cut in the graph. And this is known as the subtour elimination LP, or the Held-Karp relaxation. And note that even though I've written an exponential number of constraints here, it can be solved in polynomial time via a separation oracle. I can always find the smallest cut of the graph, and if it's below 2, I can return it as a violated constraint. And of course, this is a relaxation of the problem, so an optimal solution to this LP bounds the cost of opt. And the second piece of background, a spanning tree distribution is lambda uniform if every edge has some non-negative weight lambda e, and the probability of a spanning tree is proportional to the product of the lambda e's and its edge set. So for example, this graph with lambdas 1, 1, and 1/2 would yield this distribution over spanning trees. And it was proved in 2010 by Sadpour et al. That for any point z in the spanning tree polytope, we can find a lambda uniform spanning tree distribution in polynomial time that matches the marginals of z. So in other words, if I give you any distribution of spanning trees, we can actually find another distribution that's lambda uniform that has the same edge probabilities. And they do this using a max entropy convex program. So we can alternately think of these lambda uniform distributions as the distributions which maximize entropy, or are sort of as close to the uniform distribution as possible, subject to the constraint of matching the marginals of z. And it turns out that lambda uniform trees have properties that are very useful for TSP. So here's the algorithm we study, which up to some small epsilon is from a 2010 work by my co-author Oveskaran and Saberi and Singh. So first we compute an LP solution X to this subtour LP. And then using the fact that the TSP polytope is contained in the spanning tree polytope after a small transformation, you can just believe me here. We do this transformation to map X to a point Z in the spanning tree polytope such that Z of E is equal to X of E for all the edges. And then we use this procedure to find a lambda uniform distribution mu with marginal z. So we find a max entropy distribution that matches z. And then we sample a tree T from mu. And since z has the same marginals as x, this costs at most opt in expectation. However, T is not yet a TSP tour because it's not Eulerian. We have some odd degree vertices here. So we just make the graph Eulerian. We add the minimum cost perfect matching M on the odd degree vertices of the tree. So Christofides' algorithm, for those familiar, this one from the 70s, is the same, except instead of selecting a random tree, it selects a minimum spanning tree. And our goal now is to use properties of our tree to show that the cost of the matching is a tiny bit less than half of opt in expectation. And since the tree costs at most opt in expectation, this would give a randomized 1.5 minus epsilon approximation. I'll give a brief overview of how we prove this here. So the first ingredient is very combinatorial. Recall that the LP solution X is just some fractionally two-edge connected graph. And it turns out that the cuts in this graph that are very close to 2, which we call the near minimum cuts, are closely related to the cost of the matching. So you can think of our matching as kind of spreading out across the graph to connect all the odd vertices. And the near minimum cuts are really the ones limiting the movement of the matching. Unfortunately, there may be many near minimum cuts, so it's kind of difficult to understand and deal with them all directly. And so in the first part, we reduce to the so-called laminar TSP case, in which these important small cuts form a laminar family. The second ingredient is properties of max entropy trees. It turns out that if you look at the multivariate polynomials encoding max entropy distributions, so they're generating polynomials, they have a nice geometry, which places them in the class of so-called strongly Rayleigh distributions. And this gives us a nice range of properties. And we use many of these properties and prove some new ones along the way. And so finally, we use these tools to solve the laminar case with a kind of averaging argument. And this third part kind of presents a method for dealing with any abstract collection of constraints that has this kind of laminar structure. So to sum up, the first part gives us a concise problem to solve in the form of a collection of constraints that form a laminar family. But these constraints are not always active. So in particular, each constraint, which is given by one of these cuts, is active when a tree has an odd number of edges across that cut, which I'll explain why in a minute. So this second part gives us a range of properties about when these constraints are active. And finally, the third part uses that information to design a way to cheaply satisfy the constraints that are active, sort of on average. And so that's the high level idea. I want to jump right in and analyze the case in which the LP solution is a complete graph where every edge is 2 over n minus 1, and the cost function can be arbitrary. And remember, I mentioned the small cuts are important. So all I'm going to use about this solution is that the only cuts in this graph with value close to 2 are the vertices. Every other cut has value basically at least 3. To understand this case, I already need to use that max entropy trees are strongly Rayleigh. So this is a class of distributions due to Borsea, Brandon, and Liggett. And it's defined like this. So consider a distribution mu over subsets S of a set M. For us, these will be spanning trees over the edges of the graph. And let mu of S be the measure of a set. Then the distribution is strongly Rayleigh if its generating polynomial, P of mu, is real stable. So if you assign each element I of the set M a variable, Zi, then the generating polynomial is this object. You sum over all the sets M in the support, and you multiply mu of S times the product of the Zi's for each element I in the set. And we call a polynomial real stable if it has no zeros in the upper half of the complex plane. So if I give all of these Zi's positive imaginary part, and this polynomial is real stable, that means it cannot be 0. And this is a bit hard to wrap your head around on a first viewing, but maybe for now, just notice that for a univariate polynomial, this implies real rootedness, because in that setting, roots come in conjugate pairs, so they all have to be real. And as I said, any lambda uniform tree distribution is in fact strongly Rayleigh. And I won't go into it, but it's not too hard to show it. It basically follows from the matrix tree theorem, and that the characteristic polynomial of any symmetric matrix is real rooted. And so if you take the generating polynomial of a lambda uniform tree distribution, and you zoom in on the univariate polynomial encoding the number of edges appearing in the tree in some set F, so it'd be this polynomial here, it shouldn't be too surprising that it's real rooted. It's kind of the specialization of a real stable polynomial to the univariate case. And this lets us apply an old lemma about real rooted polynomials. It turns out that the coefficients of any real rooted polynomial with non-negative coefficients can be described by a sum of independent Bernoullis. So in our setting, this means that for any set F, there exists some number of independent Bernoullis, B1 through Bm, such that the probability the number of edges F shares with the tree is K is exactly given by the probability these Bernoullis sum to K. And I'll use this notation F sub T to denote the number of edges that set shares with the tree. So this actually gives us a really nice result. We use this in our paper to show that each near minimum cut, so each cut with X value close to 2, is even with probability at least 0.43. And to do this, basically you just let F be the set of edges in that cut, and then use this sum of Bernoulli's fact to do a simple computation. And this is pretty cool, I think. We use this, the existence of these Bernoullis kind of lets us talk about the parity of a random variable, which is a kind of claim we don't see too often. It's kind of distinct from concentration phenomena in some ways. Okay, so why am I even talking about parity? Well, remember that the matching is only over the odd vertices. So this should give you some hope. At least we know most vertices do not have to directly participate in the matching. They don't actually have to be matched. Basically something like half of the vertices should be even. So this should be, at least promising. So on the left is an example of a tree Christophidis' algorithm might pick. This is the algorithm that instead of a random spanning tree picks a minimum spanning tree. And you're basically doomed here. This could be the minimum spanning tree, but here every vertex is odd. So your matching on the odd vertices will probably be expensive. And this previous lemma says, at least we don't have trees like this. We pick trees that maybe tend to look a bit more natural. In fact, we pick trees that are as close to uniformly random as we can get. And maybe they tend to look more like this. And now we know that at least, we know formally that there are many even vertices. And this seems good, but it's not actually quite enough. The matching can still be very expensive, even if almost all the vertices are even. Think of just 2 odd vertices that are very, very far apart, and say those are the only 2 odd vertices in the tree. Then to connect them, we might have to pay a lot, maybe opt over 2. So we need something more. And we show the following. If A1 through AK are disjoint subsets of edges, and alpha I is the expected number of edges of T in AI, then if the alpha vector is close to the all ones vector, so all these things have expectation about 1, then with a probability that's a function of only epsilon and K, the tree has exactly 1 edge in all of the AIs. And we show this for any strongly Rayleigh distribution. And if you'd like, you can think of this as proving a bound on the measure of bases in the intersection of a strongly Rayleigh matroid and this kind of partition matroid. And some good news here is that while we were only able to get this crazy doubly exponential bound, independent work by Gurvitz and Leek, which you can hear about in this conference, showed that if the distribution is homogeneous when you project to these AIs, we can get something singly exponential. And unfortunately, we haven't been able to quite extend this to work in our case, but we're hopeful it maybe can be. So for the rest of the talk, just assume that this theorem implies that any K near minimum cuts are even simultaneously with constant probability. This is not quite true, but it would be true if we didn't have this word disjoint here. And it turns out to be almost always true. So I'll assume it for this talk. So given this, the case where the only small cuts are the vertices turns out to be fairly easy. But to say this, I need to introduce this object called the matching LP. So here's the LP, and here's an example tree we want to augment with a matching, where I've marked the odd degree vertices in red. And all this LP is saying is that if there's a cut with an odd number of odd vertices in the tree, or equivalently by degree sum arguments, the number of tree edges in that cut is odd, then we need to have fraction 1 across that cut. And this is obviously necessary because one of these vertices has to be matched outside this set. And it turns out that this set of constraints is enough. So this green set does not have to show up. And what's great is that this LP completely characterizes the cost of an integral matching. So to say there exists a cheap matching, we just need to find a cheap solution to this linear program. We need to send fraction 1 across every odd cut of the tree. And remember, all we're trying to do is show the existence of a cheap matching. The algorithm finds the cheapest one. So what's the cheap solution in the complete graph? First, notice that if we start off at half of the LP solution X, this is already feasible and only costs half of opt. This is feasible because the LP sends fraction 2 across all cuts, and we only need fraction 1 for some of the cuts here. And our goal is to just get a little bit better than this. So we start at this feasible solution, and maybe we'll change it a little bit to gain some epsilon, and that would be enough. And now what do we get from assuming the complete graph? It should be clear that the only near tight constraints of this feasible solution are the near tight constraints from X. But as I said earlier, in the complete graph case, the only near tight constraints with actually less than value 3 are the vertices. So every other cut is going to have the sum of the YE in this solution at least 1.5. So the only constraints that don't have a lot of slack are the vertices. So now pick any edge E. It's only in 2 cuts that sort of matter. It's endpoints. And let P be a lower bound on the probability that any 2 cuts are even simultaneously from the theorem a couple of slides ago. Then with probability P, the tree that's picked has even intersection with both of its endpoints. And so these 2 tight constraints that E was in disappear. So in other words, with probability at least P, any edge E is in no tight constraints. And in this instance, we can obviously reduce the value of YE in this feasible solution since it's in no tight constraints. So this edge gains against this initial feasible solution by some constant times P. And since P is a constant, we're done. This is what we wanted. So to rewrite this idea a tiny bit, I can start at this feasible point XC over 2 everywhere, which gives us a matching of cost half of opt. And if I want to do better, I can actually ask to add a small slack vector, which keeps my point feasible and has negative expectation on all edges. And this would give me a cheap matching. So in the complete graph case, my slack vector is just set to -1/6 when the endpoints of E are even, and this meets the criteria here. It keeps the point feasible, and it has a constant negative expectation. And it turns out the community has known how to solve this case where the only small cuts are the vertices for over 10 years. So, we have some more work to do. And one of the big issues is that the near tight constraints of this X over 2 solution, so the near minimum cuts of X, can be quite complicated, as in this picture on the left. And so, as I mentioned, we reduce to the case where these constraints look very simple. They just form a laminar family. In other words, this means we can assume all other constraints have some epsilon slack in this X over 2 solution. I don't have time to talk about it. I just kind of want to show this process visually. And for those familiar, I want to say we take as inspiration the cactus structure of minimum cuts and a generalization of that to near minimum cuts from Banksor and Gomez called the polygon representation. So now I'll say a little bit about how we solve this laminar case. So on a high level, as I said, we're going to perform an averaging process. But notice that edges and few constraints are very easy to get this negative slack for. There's some constant probability that all the cuts from the hierarchy they're in are even. And in this case, there's slack on all the constraints they're in, so we can set their slack to be negative with some constant probability. This is just the same as the complete graph case. However, edges in many constraints that go sort of very high in the hierarchy cannot employ this strategy. So instead, we decrease them when the constraints locally around them are even. So say for this purple edge, these two cuts are even, and we're going to call these kind of the top two cuts of this purple edge. Then we're going to reduce this purple edge's slack. However, there may be constraints lower down in the hierarchy, maybe these two red ones, that are active. Maybe these cuts are odd, but now we've reduced this edge's YE, and so we've broken these constraints. These now sum to less than 1 in the matching LP. But the edges sort of lower down are in fewer constraints, and so basically by induction, you can imagine they have some room to increase to make up for this edge's decrease. So that's what we're going to do. And on a high level, we know that every edge has some expected decrease because we're going to decrease it no matter what when these top two cuts are even. And now the goal is to show that the expected increase exceeds the expected, the expected decrease exceeds the expected increases from these plus epsilon steps. And to talk about this, I'm going to zoom out and look at a broader picture. So say E is an edge in many levels. What we're going to do is perform a matching such that every LP edge is matched to exactly one other edge of the same fractional value. And for any edge and any cut below its top two, it has some edge matched to it. So here let F and G be some edges matched to E. And that means that when E is reduced and these cuts are odd, we're going to increase them to make up for E's reduction. So if E is odd, E is reduced, and S is odd, we'll increase F by epsilon. And all we want to say is that each edge has negative slack in expectation despite this increase. So let's look at F. And so P is the probability that F is even in its top two cuts. And the same for E, let's say. And then F decreases by epsilon with some probability P and increases by epsilon when S is odd and the edge E is reduced. But actually, to make this less than 0, to make this negative, all we need to do is to say that this conditional probability is some constant less than 1. However, we kind of already know this. We know that any three cuts are even simultaneously with constant probability. And this is actually enough to prove that this conditional probability is below 1 because we apply this to the top two cuts of E and this cut S. So we're simply showing that within the space E is reduced, there's some small mass where S is even as well. And so the expectation of this slack goes below 0 by some constant. Okay, of course, this is a gross oversimplification of what's going on. I don't want anyone who takes a look at our paper to be kind of shocked that it doesn't look like this. But with some elbow grease, we're able to bound the cost of this matching LP and expectation, and therefore the cost of the matching as well. Now, although this epsilon improvement is very small, there's a quantitative study from Genova and Williamson which shows that max entropy trees appear to be actually much better than Christofides on a set of benchmarks. So maybe we can be hopeful. There's actually a conjecture that this is a 4/3 approximation, this algorithm. And I also wanted to quickly mention that recently we extended our analysis to show that the integrality gap of this LP relaxation is at most 3/2 minus epsilon. This is on arXiv. This is something our first result did not do. And this also kind of made the result more constructive, which may help with de-randomization, which is one open question. But the main open question is whether our analysis can be greatly improved. We still have no idea how much better than 3/2 this algorithm is. And we're very hopeful that someone will come along with an exciting new idea. So thanks for listening.